Continuing our chapter 18 mechanism discovery, we have esters reacting in both of these. And we have a new guy, as it's aluminum that only has 3 bonds. Here he is. H bonded to aluminum, bonded to 1, 2, 3 with a V, 1, 2, 3 with a V. What's 1, 2, 3 with a V? Isobutyl. What's the short form for isobutyl? IBU. What's the most common drug with IBU in its name? Ibuprofen. Guess what group's in ibuprofen? Isobutyl. Guess what the pro stands for? Propyl. What's the fen stand for? Phenyl. What's ibuprofen? You do need to know, it's not in the name, that the groups are para. Ibu. There's your phenyl. Propanoic acid is the pro. There you go, ibuprofen. Has nothing to do with our mechanism, but everything to do with IBU. Okay? And what happens in this one is we're going to go red first, blue second, and we're going to be pretty much done. It's an easy mechanism. H minus really doesn't happen. It's like these are simultaneously that attacks with its electrons, and then the pi breaks and comes back to aluminum, and you get an intermediate. You got to know this is not as reactive as when there's a H minus, okay? Because there's no minus. So we got O bonded to aluminum with your 2 IBUs. You got your new H. Sorry, switch the color scheme on you here. And we have an OET. And that is actually the end of step 1. This thing doesn't have extra H's or anything to be more reactive. It's neutral, it's pretty stable. Everything here is pretty stable, so it stays. HCl is going to break this thing down. So let's make sure we get everything accounted for. HCl, we're on step 1 is over, step 2 is beginning. Ethanol, not a good leaving group. So guess what the first step is? Protonate it, make it a better leaving group. That broken record's still around, isn't it? And you want to do your Cl minus that you just made? Of course you do. Look, aluminum has a chloride, right? And you do know that you're not going to do an SN2 here. Aluminum's nature is just to accept a 4th bond and then make an intermediate. And the next step, you'll break the 4th bond. That's aluminum and boron's nature. And a 3rd color will help you finish the mechanism. Leaving group leaves. Pi generates. Everything done. Okay? That's step 2. 3 steps in step 2. We're really making up for that mechanism where we didn't even use HCl, aren't we? Okay. Switching up to Grignards, our old friends. Grignards, and what reacts identically to Grignards? Organolithium, so we could have replaced this with or lithium attached to IBU. No, that's isopropyl, sorry. Isopropyl. They both do the same job. In both cases, you're going to cross off the spectator. Put a lone pair on the carbon and make sure you know that's really a carbanion. And we're going to do our deal that we've been doing all day. Attack the carbonyl, generate a lone pair. Lone pair comes back, kicks off the leaving group. And you're saying to yourself, wait, O- is a terrible leaving group. We are currently in a reaction that started with the worst leaving group known to man. Do you think I mind replacing that with a lot better leaving group, even though it's bad? Think about it. This is chemistry. This is how things happen. You take a terrible situation and make it just bad. That's a driving force, seriously. Okay. Here we go. Carbonyl. It's an aldehyde. No, it's not. There's a new group on there. It's not an aldehyde. Got this new exciting bond to an isopropyl. It's a ketone. We're not done, are we? Hey, chapter 16. Ketones react with organolithiums and Grignard reagents. This is the chapter 16 reaction, starting now. Hey, more broken records. I'll be with you in a second, Mr. Arbit. Another broken record. Uh-oh, I lost my train of thought. Oh, it's back. Ketones are more reactive towards organolithiums and Grignards than esters are. So guess what happens next? Here's your two choices. Does the organolithium attack ester number 2, or does it attack ketone that you just made? Ketones are more reactive. They will react first. And Mr. Arbit has a question. I'm missing a carbon? Nah, because I rotated it. That's what happened. And then we need a second isopropyl anion. So here it is. You ready? There's excess, so don't worry. Don't ask where it came from. It was there. Chapter 16 mechanism. No leaving group here, so don't have those electrons come back. There's no leaving group. They're going to stay up there. And you've got your old isopropyl from before. And you got your new isopropyl from now. So yeah, if you want two new identical groups on a carbonyl, start with an ester, hit it with an excess of organolithium or Grignard. And then you'll end up with an alcohol, that's our goal, an alcohol that's got two identical R groups on it that weren't there before. We're calling this synthesis. This is great. We love synthesis, right? Well, we pretend to because we know it's important to Dr. Whitaker. Okay. So a reminder, you generated O- ethyl here, and I think we can finish the mechanism. Step 1 is here and here. It's time for step 2. And I don't even need to explain myself here, do I? HCl, and I don't know, side product, we'll go light pink. It's gonna go here. HCl, same story. Acid base, acid base. Uh-oh, I got arrows, crossing reaction arrows, oh boy. Need to put some traffic lights in here. Okay. And that's esters reacting with hydride, special hydride. Oh, I didn't tell you what it's called. Its short form is, let's make it look nice. I haven't used one of these in a while. DIBALH-H. Oh, not much room for an H. And if you want to write that out, diisopropyl isobutyl aluminium if you're British, hydride DIBALH H. It's far from diabolical. Very useful. Okay, that's the end.